I'm Lee Samin, the group leader of Group 7, and our group consists of two other members, Guo Zenan and Kong Xiaoyu. Guo Zenan will be explaining on the classification techniques, and Kong Xiaoyu will be explaining on the anomaly detection, and me myself, I'll be explaining on the regression and clustering data mining techniques. I'm Lee Samin, and I'll be walking you through the code linear regression. Now, we use linear regression for analyzing high-risk period in our data set. So that was our analysis objective. Now let's move on. So first, we start off by importing necessary libraries, loading the data, and doing an overview, checking the data type, null values, and column names at a glance using dfinfo. Now, since date is an object data type, we convert the date to datetime format. Then using date, we create a year-month column, which is an aggregate column by month. We only used year-month because including day is too specific, and only year or month is too broad, which doesn't capture the intricate details of the time series nature. Now, after we do that, we aggregate the data by month, year-month, to get the death count per period. As you can see, the aggregated data frame shows year-month and death count. Then we convert the year-month to datetime and then to a numerical value, which is the ordinal. Now, time index is an ordinal value. Doing this is a common practice in time series analysis to make the time-based data more compatible with models and to capture the temporal relationships within the data. Similarly, death count lag 1 represents the number of deaths from the immediately preceding period. This is used to capture temporal dependencies in the data. Other transformations that we did include month sine and month cosine. This is a nonlinear transformation applied to help the model capture seasonal and cyclical patterns in the data. Then we use capping to handle outliers. We only cap the upper threshold as the lower threshold is considered to be natural occurring. For example, the death count of 0 is considered naturally occurring. Capping these values would introduce artificial bias to the data. Now then, we prepare the features and the target. The features that we've used was time index, month sine, month cosine, and death count lag 1. And the target variable we use is death count. Now, let's split the data into training and testing sets, which split them into 8:2 ratio. 20% is aligned and assigned to the test set. There's no specific reason to do this, but 7:3 and 8:2 is usually the typical ratio. Now, we apply standard scalar to minimize the effect of outliers, and we only transform the x-test without fitting it to prevent data leakage. We then initialize and train the linear regressor and then predict using the test set. Then we evaluate the model performance using the 6 metrics that you can see below. We can assess the model accuracy by looking at the adjusted R-square, which is 0.9. This is a very good score and indicates that it's a very accurate model. MAP adds to this as the error that the model shows is only 11%, which is in an acceptable range. However, MSE is 102, which shows room for improvement and possibly better outlier handling methods. The below visualization you can see is a plot of actual versus predicted along the regression line. As you can see, everything is fitted quite okay. However, the 100 and 120 range shows a few outliers. We plot the residual to show the reliability of the model. Now, the residuals doesn't show any distinct shape of funnels. This means the model is also reliable. Now, we move on to analyzing the top 10 periods as the model result validated the use of any death counts above 130 or below 100. Now, luckily, our top 10 periods only show death counts above 130. Now, let's analyze these death counts. So, the most frequently seen year is 2021. This is likely due to the year 2021 being COVID-19's peak period. Then we see the late quarters, September, August, October. These months indicate that at the late quarters, companies tend to mass lay off individuals and employees to increase shareholder value and decrease cost. This can have a lasting socio-economic impact. And also, in the late quarters, people tend to suffer from depression or mental health issues, maybe due to a lack of sunlight, as is during winter. Furthermore, we can see that in 2021, we can assume the disruption in the healthcare system during the peak of COVID-19, but also the underlying drug trade and the rise of fentanyl. Now, let's move on. To validate the model, we have to see if it satisfies the assumptions. The first assumptions we can check for is the linearity. The plot shows that the model satisfies the assumptions of linearity, although obviously month sine and month cosine is not linear as nonlinear transformation was applied. Now we then check for homoscedasticity. Now we can use the visual method and also the Bruch-Pagan test. Now we're going to be focusing on the Bruch-Pagan test. The Bruch-Pagan test is at 0.885, which well exceeds our p-value of 0.05, which means there's no heteroscedasticity. Now we move on to visualize the normality, the distribution of the residuals. We use histogram to do this. As you can see, our histogram is pretty symmetrical and shows a moderate bell-shaped curve. Furthermore, our QQ plot is pretty well aligned with the red line, which shows that it follows the Gaussian distribution. We can further do a Shapiro-Wilk test, and we can see that it passed the Shapiro-Wilk test and concluded as the normality is being met. Now, we can test for multicollinearity using the various inflation factor. Fortunately, the features only exhibit 1 or 7 VIF, which is well below our set threshold, which is 10. Now, although the independence is assumed to be satisfied due to the time series nature of the data, but we still perform the test using Derby-Watson test. The Derby-Watson statistics show 1.98, which is a close value of 2. This suggests that no autocorrelation is present. That's it from the linear regression, and I'll see you in another section of clustering. On this segment, I'll be walking you through my second code, clustering of k-means. Now, the analysis objective tackled in this code with this model is to analyze high-risk groups. More broadly, analyze the trend in drug overdose. Let's start. So obviously, we always start with importing the libraries and overviewing the data. As you can see, this is the general overview of the data. And now we proceed to the most important part of k-means. And the reason why this is the most important part is k-means assumes continuous variables for their features. However, the dataset is full of categorical or binary variables which are not continuous but discrete. So adequate transformation has to be used. We can use different algorithms like k-medoid or k-mode or even dbscan. However, we wanted to explore how k-means perform and what kind of insights it can give. Because in many literatures, k-means is deemed to have the highest performance and is more widely adopted in the healthcare and the medical industry. So now let's start. So first, we gather the opioid columns, but because we want to investigate whether the opioid consumption has anything to do with the demographic variable age. So now we gather the opioid columns and we combine them with the age feature. So this is one feature, and we investigate. So as you can see, everything is in object form, so we have to encode them. Since those are in yes or no, so we encode them in 1 or 0, yes to 1, no, or pending to 0. So now we can check for the missing values. Fortunately, there's no missing values during the conversion. So we can proceed. Then we create a new column called opioid count. So as you can see, if let's say fentanyl and let's say heroin is yes, then there'll be 2 counts. Then we retain only the 2 required columns for the analysis by dropping all the other opioid columns that we gathered just now. Now we can pre-process the dataset. We use min-max scalar instead of standard scalar because there's no outliers. And also, min-max scalar preserves the relationship between the minimum value and the maximum value very well. So the order of the relationship. So that's why we use, and then we rename the opioid count to opioid consumption for further pre-processing. Now, before we do that, we have to see the distribution of age. So the age seems pretty continuous. However, we can see that the distribution of opioid consumption is very discrete. This is not ideal for k-means. So what we do is we use Gaussian kernel smoothing. This is an approximation technique to convert discrete to continuous. And the reason why we use Gaussian kernel smoothing is because it's deemed to be more convenient and exhibit the highest performance. So we apply the Gaussian filter. And we finally apply the quantile transformation. Although normality is not strictly urged for k-means, it's still good to have a normal distribution or anything close to that because a lot of the statistical techniques rely on the normality. So after the quantile transformation, we can observe the distribution of opioid consumption. First of all, it's continuous. And second of all, it seems to be close to Gaussian distribution, although we can't be exactly sure if it's normal. Now, we can start moving on to the decisions of the optimal K clusters. So we use the elbow method within cluster sum of squares method. And as you can see in this plot, 3, 4, 5 seems to be the most optimal K clusters. This is really entirely subjective to trial and error. So after trial and error, we deem that best K is 3. So now we fit the model and we predict the data set using k-means. So after that, we visualize the clusters. As you can see, it seems that the clusters are well separated or arbitrarily stacked. This may mean that there's no inherent relationship between the opioid consumption and age. So let's say if we were to formulate a hypothesis that age affects the opioid consumption, this would be wrong. So this is one benefit of k-means clustering, or any type of clustering, aids in the hypothesis formulation. Now we validate and evaluate the clusters. So the DB index seems to be 0.65. So the closer it is to 1, the worse it is. So the lesser it's better. The silhouette coefficient is 0.47, seems to be moderate, but the Kalinske-Harbis index is very high. So we can see that overall the cluster is okay, but there are room for improvements. Now, although it's not really typical and classical to use decision tree to understand the clustering logic, but since we want to understand how the clusters are formulated, decision trees can be used to understand the post-cluttering logic. Although this may be there may be a downside in using decision tree as it imposes a supervised learning logic to an unsupervised learning logic like clustering. But we can still see that this tree shows that opioid consumptions play a very heavy part in deciding the clusters, and only in some part age gets involved. And the effect is very minimal as it only plays with the 6 samples out of 11,000 samples. So as you can see, the cluster is okay, and we can finally conclude that opioid consumption is not really affected by age. That was it for me, and thank you so much.
Hi everyone, my name is Guo Zenan, and I will introduce our classification and training part. The algorithms we use in our classification part are SVM and KN algorithms. So our research on SVM algorithm objective is to predict whether cases have tiny usage based on demography and geography information. Our KN's objective is to predict whether there is cocaine intake. The data set we choose is our data set after assigning one cleaning, which can help us perform machine learning steps more efficiently because it already been cleaned properly. So first, we import all the necessary libraries we use for our SVM work. We have got pandas and NumPy for data handling, Matplotlib for creating visualization and several skin learning modules for our machine learning tasks. These include tools for splitting our data, pre-processing it, building SVM models, evaluating the results, and reducing damage using PCE. We also bring in a small from imbalanced learning to help with class imbalance issues. Then we load our dataset and check it by hand function. Here we can see we upload successfully. Then we define with columns with features we were using our model. First, we undefined demographic and location features right here. Next, we list our drug columns we will analyze. Then we convert all these columns to binary values. So y becomes 1 and everything else becomes 0. Finally, we check the first few rows of them. And we can see we selected successfully. Then after that, we're gonna create a feature called other drug count, which count how many drugs except fentanyl involved in each test cases. We also set a using fentanyl, which is our target variable, and we're trying to predict it. Then we check our new columns right here. We move it successfully. About our feature engineering, it's basic feature engineering. Right here, we prepare our data for modeling. We select our features handling machine values by dropping them, convert category data to numerical using one hop encoding and standardized numerical features like age and drop count. This pre-processing is crucial for our SVM model. From the hand function output, we can know that all the new data has been transformed. Now we move to our model training part. We split our data into training and testing separate. So 80% for training and 20% for testing. Because there is an imbalance of our data set, so we then apply small technique to handle class imbalances by creating semantic samples. So we create our SVM classifier with a basic function keyner and train our balanced data set. From the output, we can see that our model trained successfully. After training, we will move to our basic testing first. It's our model evaluation and the validation part. So we test our model on the test data, then evaluate the performance. Here we can see our SVM accuracy is 64%, and balance accuracy is 61%. The classification report says we are better at predicting fentanyl using 35% presence and 30% recall compared to predict non-use, which non-use is O. And F1 score is 0.32. Is for detecting fentanyl involvement. And after that, we move to our visualization testing. Here we visualize our model performance with a confusion matrix head map. We can see that in the actual fentanyl cases, our model correctly identify 1,119 cases, but basically 400 and little cases for non-fentanyl cases. We correctly identified 405 cases, but had 334 false positive. This is dark blue in the bottom right, shows our multiple performance of assays. And then finally, if intercontaining presence, it indicates potential value for preliminary scanning, but with room for improvement, some improvement. For the visualization test two, second visualization, we created ROC crave, which about the trade-off between true positive rate and false positive rate at different classification. Our crave has an area under the AUC of 0.67, which indicate moderate predictive power. The crave above the diagonal line shows our output performance better than random guesses. And there's still room for improvement. For our final SVM module visualization, first we use PCA to reduce our high dimensional data to just 2 dimensions, so we can plot it easier. And the plot compares the true Fontana use, which on the left side, with what our model predict on the right side. The right points indicate Fontana use, and the blue points show non-use. So the similarity between these point plots indicate our model is capturing patterns in the data, and there's still some mixing of red and blue points, which reflects our accuracy. It reflects our accuracy of around 64%. So our visualization help us understand how well our model distinguishes between classes in a simplified 2D space. It's not that high accuracy. We think that it's maybe our data set original question, because it's quite hard to predict whether a cases is using because of the complex situations. So that's our SVM algorithms. Okay, now we move to our KNN part. For our KNN module, we import some additional libraries for our KNN. So right here, KNN neighbors classifier is a core kernel we use along with matrix to evaluate performance. Random under sample helps balance our classes by reducing the major class, where pipeline lets us combine processing and the modeling steps. List color map give us color over the colors in our visualization. After we upload the dataset again and check it through the hand function, it's the same as SVM. Here we can see we import upload successfully. After that, we select our drop related columns, then we convert them to binary format. It's convenient for and it must for our visualization part. And after drop related chosen, about the feature, we select the information about the demographic and location. And our objective by KNN is to predict whether cocaine is used, and also our target value is cocaine. We select it, then we prepare feature matrix and target vector. After that, we drop missing values. Right here, we drop missing values. Then we select, we make one hot encoding for our category data, then sterilize the numerical feature age. So the hand function to see right here, we pre-processing them all successfully. Then move to our KNN model training part. We select the data first. We discover imbalance like right here with about 38% of cases involving cocaine. So we apply random under sampling, which reduces majority class. Given us a balance 50-50 distribution, we then train a KNN classification with 9 neighbors and distance weighting, allowing closer neighbors to have more influence on our predictions. So we can see we train the model successfully. About the prediction part, the first we can see right here. We test it and we see the accuracy is 58%, 58.5% with better performance and that it identifying non-cocaine cases, 65% and 30% recall, then it's better than cocaine persons. About this part, our confusion matrix map visualizing confirms that what we saw in the classification report, the logic is in with SVM we just introduced. We correctly identified 1,036 true natives. That's no cocaine, but at 551 false natives where cocaine was present but missed. And this suggests that, well, the dataset has moderate predictive power. It's more reliable at ruling all cocaine involvement than confirming it, which could limit its practical utility in identifying cocaine-related dyes. So our KN visualization shows decision boundary of KN models. It's done after our PCA project. It's done after that, which reduce our data to 2 dimensions. The blue area indicate the predicted cocaine presence. Training points show as cycles and test points at X makers, with red for no cocaine and blue for cocaine. The complex alternating pattern of the decision boundary shows why our data has moderate performance. There's significant overlap between the classes, making it difficult to clearly separate cocaine from non-cocaine cases based on demographic and location features alone. Since we have pre-processed data set balancing, but this actually solves the limitation of our data set itself and the single key and operation in the target node size. So we will reprove it better. That's all for our classification part. Thank you.
My name is Kong Yayu, student ID 0369375, and I'm responsible for the anomaly detection part of this assignment. So now I will start with the setting part section. So I set up the environment by importing essential Python libraries for data manipulations, modeling, and visualization. Specifically, I use pandas and NumPy for handling data and numerical computations. From scikit-learn, I import the standard scaler for scaling features, local outlier factor, one-class SVM, and isolation forest for anomaly detection, along with train test split, accuracy score, and F1 score for splitting the data and evaluating model performance. Additionally, I use matplotlib for visualizing the data and results. After setting this up, I load the dataset named accidental drug-related deaths clean using pandas. Next, I will continue with the dataset overview part. So, I perform a quick overview of the dataset to understand its structure and the kind of data we are working with. Here, I use the head function to display the first 5 rows of the dataset. Next, I print all column names to get a full list of available features. This will help me decide which columns would be useful for anomaly detection. Next, I will go to the pre-processing part. So the first step was to select the relevant features for anomaly detection. From the full dataset of 39 columns, I selected 22 columns that are directly related to the age and drug involvement. This includes substances like heroin, fentanyl, cocaine, and others, along with age, since these factors are highly relevant for detecting unusual drug-related deaths. Next, I also create a new dataset named dfSelected that contains only these selected columns. After selecting the columns, I display the first 5 rows to verify that the dataset is correctly filtered. Next, I will go to the data cleaning part. So first, I checked the missing values in the selected dataset. I found that the column other substance had 11,361 missing values, while the rest of the columns were complete. To handle this, I use a custom approach that I treat the missing values as N, meaning no drug detected, and non-null values were converted to Y, meaning drug present. Next, I also explore the unique value in each column. Then in the ethanol column, we can see that it consists of p-value, means this is not expected, and we will try to fix it. So at the last, to maintain the consistency, I replace P with N, assuming it indicated absence of ethanol. After this fix, all values in ethanol were properly labeled as Y or N. So next, I will continue with the handling duplicate data. Next, I check for any duplicate rows which can skew analysis and model results. I used the duplicated function to identify duplicates and then counted how many rows were affected. As shown here, the results were 0 duplicated rows, so no further action was needed in this step. Last, I will go to the data transformation part. Before transforming the data, I first check the data types of each column. As shown here, the each column is correctly identified as an integer. However, all other columns, including the drug-related ones, are labeled as object because they contain category values like Y or N. So I will go to the transform data part. First, I convert all drug-related columns, which have values Y for yes and N for no, into numerical format, where Y becomes 1 and N becomes 0. This step is important because machine learning models require numerical input. Then I verify the transformation by displaying the first 5 rows. As you can see, the columns now have binary values of 1 and 0. Next, I will go to the normalized data part. So in this part, for the each column, I use standard scaler, which transform the values so they have a mean of 0 and a standard deviation of 1. This step ensures that the age is scaled properly, has the same influence as other features in the model. If we skip this, models could bias toward unscaled values. After normalization, I printed the first few rows again, confirming that age values are now standardized. So I will go to the anomaly detection part now. So in this part, I have used 3 methods. The first anomaly detection method I use is one-class SVM, which detects outliers by learning boundary of normal data and labeling anything outside it is an anomaly. I use RBF kernel for nonlinear patterns, gamma equals to 0.1 and NU equals to 0.1, meaning the model expects 10% anomalies. After fitting the model, it labeled 1 equals to normal and -1 equals to anomaly, and detected 1,189 anomalies out of 11,896 cases, roughly 10% as expected. I also displayed the first 5 anomalies. These were unusual cases based on age or drug combinations. Next, the second one is isolation forest model. So isolation forest models, which detects anomalies by isolating data points using decision trees. I use 100 trees contamination equals to 0.1 and a random state for consistency. After fitting the model, it labeled 1 equals to normal and -1 equals to anomaly. It also detects 1,190 anomalies, almost identical to SVM, confirming the consistency. Again, I show the first 5 anomalous rows, highlighting statistically different case. Last, local outlier factor. Local outlier factor, which detects anomalies by comparing each point to its neighbors. I set 30 neighbors contamination equals to 0.05, expecting 5% anomalies. After fitting the model, it also labeled 1 equals to normal and -1 equals to anomaly. It detected 595 anomalies, about 5%, and I also displayed the first 5 rows of anomalies. These represent localized outliers, cases with rare drug patterns or unique age that are unusual within their local context. So now I will continue with the evaluation and validation part. I first convert the model output so that 1 means anomaly and 0 means normal for all models. Then I created a baseline using majority voting. If at least 2 out of 3 models flagged a data point as an anomaly, it was marked as an anomaly in the baselines. I evaluated all 3 models using accuracy, precision, recall, and F1 score by comparing their results to the majority baseline. Accuracy metrics. Accuracy metrics measure overall correct predictions. SVM had the highest accuracy, 95.25%, followed by isolation forest at 94.83% and LOF at 90.57%. Precision metrics measures how many predicted anomalies were correct. SVM and isolation forest had similar precision, 53% and 51%, while LOF was much lower, 9.5%. So the third one is recall metrics. It measures how many actual anomalies were detected. SVM had excellent recall, 98.75%, isolation forest at 95%, and LOF only have 8.9%. So the last one, F1 score metrics, balance, precision, and recall. SVM achieved 69%, isolation forest 66%, and LOF again lower at 9%. And now I will continue with the validate part. So to validate the models, I use 2 approaches, semi-supervised and train test split. In semi-supervised part, I separate normal and anomaly data based on the majority baseline. Then I split the normal data into training sets to 80% and testing sets to 20%. There are 512 records for training and 128 for testing. I combined 128 normal test case with anomalies and tested all models. Results show that SVM and isolation forest correctly identify more anomalies compared to LOF. And now I'll continue to train test split. Here, I split the entire dataset into 80% training and 20% testing. Also, there are 9,516 records for training and 2,380 for testing. Each model was trained and tested again. The results were consistent. SVM and isolation forest detected most anomalies, while LOF detected very few. Last, I will go to the visualization part. To compare the evaluation results visually, I create this bar chart showing all 4 metrics: accuracy, precision, recall, and F1 score for each model. From the chart, SVM and isolation forest both had high accuracy and recall, around 95% or more. However, SVM had the highest F1 score, showing the best balance between precision and recall. In contrast, LOF scored much lower across all metrics, especially precision and recall, indicating weaker performance. The visualization clearly highlights that SVM performed the best overall, followed closely by isolation forest. Then the second bar chart is compare how each model performed in semi-supervised validation and train test split validation, showing the number of anomalies and normal cases detected. In semi-supervised validation, which is lighter colors, all models were tested on a small set of 128 samples. In train test validation, which is darker colors, they were tested on 2,380 samples. From the bar chart, we can see that SVM and isolation forest consistently detected more anomalies both in small and large datasets. LOF detected the fewest anomalies in both validation methods. This visualization confirms that SVM and isolation forest are more reliable, while LOF underperforms across validations. That's all. Thank you.